All right, this is part 3 of the chapter R material, and we're picking up with rationalizing the denominator. So what it means to rationalize the denominator is we want to get rid of any square roots in the denominator. And the way we do that is by multiplying by the conjugate of the denominator. The conjugate of the denominator keeps the denominator exactly the same. The only thing that changes is the sign in the middle. So that 5, if it's positive, stays positive. If it were negative, it would stay negative. It's just the sign in the middle that switches, and we multiply by that over itself because that's essentially just like multiplying by 1. Anything over itself is 1, and we can do that. So now it's just a matter of multiplying those out. I like the box method. If you like FOIL, go ahead and FOIL. On top we have negative 3 plus square root 2, and then we have 5 plus square root 2. 5 and negative 3 is negative 15. 5 square root 2, negative 3 square root 2, and square root 2 times square root 2 is 2. That's the square root of 4, which is 2. So on top, I have negative 15 plus 2 is negative 13, and negative 3 root 2 plus 5 root 2 is 2 root 2. And then on bottom, what's really special about these conjugate multiplication problems is the middle terms cancel out. I have 5 minus root 2 and 5 plus root 2. This is 25. This is negative 5 root 2. This is positive 5 root 2. Those cancel out, and then I have negative square root 4, which is negative 2. Well, 25 and negative 2 is 23, and that's my answer. You can split these up and write it as negative 13 over 23 plus 2 root 2 over 23 if you'd like. Either way is fine. All right, let's move on to the next page. And now we're looking at polynomials and multiplication of radicals. So let's kind of start off with some definitions here first. A monomial is a polynomial with just one term. Binomial is 2 terms, and trinomial is 3 terms. A degree of a polynomial is the highest exponent of the polynomial. This is the general form of a polynomial. It always seems to scare students because there's a lot going on here, but it's actually pretty simple. We'll talk more about this definition when we get into chapter 3. All right, so we have some special products here. If I have a plus b times a minus b, these are conjugates of one another. I end up with a squared minus b squared. Middle terms cancel out. If I'm squaring a binomial, this is what I'll end up getting, or you can just use the box method or FOIL. Cubing a binomial, here are my formulas. All right, let's do some examples. So when I have multiple things to multiply here, I choose 2 of them to start with. And I can use my box method here, and this is why I like it better than FOIL, is because I can use it regardless of the size of the polynomials. So 2x plus 2, negative 2x squared minus 5x plus 1. Multiplying here, I end up with negative 4x cubed, negative 4x squared, negative 10x squared, negative 10x, and 2x and 2. And combining like terms, I have negative 4x cubed, negative 10x squared, and negative 4x squared is negative 14x squared. Negative 10x and 2x is negative 8x, and then 2. But remember, we still have a negative 3 out front, so now I have to distribute that. So this becomes 12x cubed plus 42x squared plus 24x and minus 6. Now when we're multiplying radicals, I can still just use a box. Negative 5 and 4 is negative 20. Negative 5 and negative 2 root 3. This is outside of a radical, so those pieces go together, and that's 10 root 3. 4 and 7, 28 root 6. And then negative 2 and positive 7, those numbers out front get multiplied, so that's negative 14. And then 6 times 3 is 18. So we can go ahead and write negative 20 plus 10 root 3 plus 28 root 6. These cannot be combined because they're not like radicals. Their radicand is different. And then minus 14 root 18. There's only one thing I need to do still is 18 is 9 times 2, so I can pull that 9 out. And that'll be a 3 on the outside. So 14 times 3, as we already saw, is 42. That's it. There's nothing for us to combine in that one. All right. And last page in this section, now we are at factoring. And this skill of factoring you will see in every section of this whole course. So it's really important that you are comfortable and master factoring. First way of factoring we're going to look at is factoring by grouping, and that's literally what we're doing here is we're grouping the first two terms and the last two terms. And in each of those groups we're looking for the GCF. So the GCF between these two is x squared. The GCF here is negative 2. And what we want is for these two to be the same. And we're going to pull those out front. We have x plus 6, and what's left is x squared minus 2. And that's factoring by grouping. Now, everybody has their own method for how they teach, or all teachers have a way of teaching factoring trinomials like this. I use what's called the X method, and I'm going to go through that with you here. And I also have more videos on my YouTube channel. If you, on my YouTube channel, search factoring, you'll find more examples of this. I really like this method. If you have a method you really like, use your method. If you don't like your method and you feel like you're not getting factoring down, give the X method a try. So, first thing with the X method is you always want to look and see, is there a GCF you can pull out? Yes, I can pull out a factor of 2. And now with this, I'm going to be using the general form ax squared plus bx plus c. And I'm going to use this kind of diamond here that a lot of people use for factoring. And you want your a times c up top and your b term on bottom. And I'm looking for two numbers that multiply to this and add to this. So a times c in this case, 3 times negative 5 would be negative 15 and negative 2. And negative 5 and 3 multiply to negative 15 and add to negative 2. And in the next step, you're going to write ax plus each of those numbers that we just found. Now, this is where my method differs from other teachers. So here my a term is 3, so 3x minus 5 and 3x plus 3. Now, if I leave it just like this, I have an extra 3 in here because if I multiply these back out, I'd get 9x squared, and obviously that's too much. So to figure out where your extra 3 is, I do what's called taking out, the step I call taking out the trash. That's just what I call it. And in this way of factoring, we're looking for which one of these factors has an extra factor or extra common factor. 3 and 5 don't have a common factor, but 3 and 3 have a common factor of 3, and that's where the trash was. So there was an extra 3 here that shouldn't have been there. We can't forget that 2 we had out front. And there we go. Now, if you want to check your answer, you can always use the box method to multiply this out and see, do you get back to the original equation, which if you did that for here, this one, you would get back to that. Now, there are also special factors for factoring, not just multiplying. So here we have some formulas. If I have a difference of squares, this is what it factors to. Sum of cubes, this is what it factors to. And a difference of cubes, this is what it factors to. So we're going to go ahead and use the formula here. We have a difference of cubes, so that's this last formula here. I'm looking for what is my a value. My a value is the cube root of this term. Well, I'm actually missing something first. The first step in any kind of factoring is always pulling out the GCF. And 81 and 24 have a common factor of 3. And now these are perfect cubes. So my A value, let me actually write it over here, is 3x. It's a cube root of this term. And my B value is 2y. So now I'm just literally plugging into this formula for my A and B value. I don't want to forget the 3 out front that I factored out. A minus B will be 3x minus 2y. A squared, 3x squared is 9x squared. A times B, 3x times 2y is 6xy. And then B squared is 4y squared. And it's factored. You're just using a formula. Last page. Rational expressions. So when we're talking about rational expressions, one of the things we need to always remember is that we can never, ever, ever in any level of math ever divide by 0. So we're going to talk more about the domain and range and restricted values. So a rational expression is just a polynomial over a polynomial. The domain is all our possible x values or our input. Range is possible y values or output. Restricted values are values that would make this undefined. In other words, what would make the denominator 0? Let's do some examples. These are the directions for simplifying rational expressions. Multiplying rational expressions, we always want to factor the numerator and denominator, cancel out common factors, and then multiply the remaining factors. So the first fraction here, there's nothing for me to factor or anything. The second one, I can factor the top. And the bottom, I can pull out a common factor. And now it's just a matter of canceling things out. Now, when it's in this multiplication form, I can cancel across fractions. But if it wasn't multiplication, like lower down here when we get to division, I could not do this when it's in division. And all I'm left with then is x plus 1 over 3. All right, next one. Now we're dividing. There's only one additional step with dividing from multiplication, and that's that the second fraction has to flip. So I can factor the top, and you could use the x method. I'm going to jump straight to the answer just for the sake of time. And on the bottom, we can factor. And then we flip this fraction and change it to multiplication. So now it's multiplication, x plus 3 on top, x minus 4 on bottom. And now that it's multiplication, I can cancel across fractions. So x plus 3's cancel, x minus 4's cancel, and I'm just left with x plus 2 over x minus 3. Now, a very common mistake I see here is people say, oh, I can cross out the x's and my answer is negative 2/3. That's wrong. This is an entire factor. They have to stay together. This stays together and this stays together. Unless the entire thing is identical, you can't cancel it out. Just like what we were doing here, we canceled whole factors, not individual pieces. So you can't just cancel out random terms. I can't just cancel out x squared and x squared. It doesn't work like that. Factors have to be canceled as whole factors. So this is my answer. Now, when we're adding and subtracting rational expressions, just like when you added and subtracted fractions back in elementary school, you always have to have a common denominator. So when I am adding and subtracting rational expressions, the first thing I want to do is factor them. Or the denominators at least. And then this one will be x plus 1, x minus 1. Now, if I want to find what my common denominator is, it needs to have all of these factors in it. So it needs to have an x plus 1 and an x minus 1. And it needs to have both of these. Well, it already has an x minus 1, but it doesn't have an x plus 2. So this is my common denominator, and I need to multiply by whatever it's missing. So this one is missing the x plus 2. I need to multiply it on top and bottom. And this one is missing the x plus 1. So now this becomes x plus 3 times x plus 1, and if I either FOIL or box that out, I have x squared plus 4x plus 3 over my common denominator. Plus, and then 2 can be distributed here. And now we have a common denominator. We can combine these terms together. So I have x squared, 4x plus 2x is 6x, 3 plus 4 is 7. And just like when you were in elementary school, you always wanted to reduce your answer. So if it's possible to factor the numerator, we need to factor and see if any of the factors reduce with the denominator. In this case, the numerator is not factorable. So this is my answer. All right, last example in this section, or in this chapter. Here we have what's called a complex fraction, and it's kind of hard to see, so I'm going to zoom in a little bit. Hopefully you have the notes in front of you and can see this. So here we have, again, a fraction minus a fraction on top of the same thing again. Now, there's more than one way to solve this, and there's actually a shortcut to what I'm going to show you. But the way I'm going to show you, you can use for any complex fraction. And so I think it's more beneficial to see a method that will work anytime you have a complex fraction. So the top is 1 over x minus 3 over 2. And then we have that divided by the denominator. So this expression means the exact same thing of what you see here, but it looks less complicated. Now, following order of operations, we work inside the parentheses first. And in order to kind of work with this, I need a common denominator. So I'm going to multiply by 2 over 2 and x over x. And here I'm going to multiply by 4 over 4 and x over x. And this will become 2 minus 3x over 2x, and then 4 plus 3x over 4x. And now we have one fraction here and one fraction here. And now this is like what we were doing on the previous page where we were dividing rational expressions. When you have multiple fractions in here, we can't just flip the second and multiply. But now that this is one fraction and one fraction, now we can flip the second and multiply the second fraction. And there's no factors here that can cancel out, but I can reduce this 4x and 2x. The x's can cancel and the 2 and 4 can reduce. So my final answer here will be 2 times 2 minus 3x over 4 plus 3x. And there's no identical factors for me to cancel. I can distribute that 2 if I want, or you can just leave it like that. And that brings us to the end of Chapter R.